Hi, it's Kamgal. In this video, we're going to perform Oxymercuration Demercuration Synthesis. Later on, we're going to perform the mechanism. In case you didn't know, Hg is mercury, and OAC is just a fancy way of drawing acetate. Don't let the fanciness confuse you. It's actually pretty easy. Whenever you see these reagents, all you need to do is redraw the structure, break the double bond, and attach an alcohol group onto the more substituted carbon. So this is a Markovnikov reaction because we are adding the alcohol to the more substituted carbon. So when the double bond breaks, these two carbons are left vacant, and the alcohol group goes to the more substituted carbon. And because it does, we say that this is a Markovnikov reaction. So now you can try the rest on your own. And if you got these products, your answers are correct. Now, we have to remember that this reaction, like others, forms racemic products, meaning that the alcohol can form on a wedge or on a dash. And so we must draw both of these possible answer choices in order to get full credit. So take a moment to draw the racemic products for each of these answer choices. Now let's talk about reagents. The stuff on top of the arrow is the oxymercuration part, whereas the stuff below the arrow is the demercuration part. This is also referred to as the reduction step. That might be ringing some bells in your ears because we know that NaBH4 is actually a good reducing agent and can reduce a lot of things. So let's go ahead and draw out the mechanism so we can see what we mean by this. In the first part of the mechanism, we have HgOAC2. Initially, the alkene is going to attack the mercury group, and the mercury is going to simultaneously attack this alkene. This results in the OAC group leaving. And can you guess what this forms? This actually forms a bridged intermediate. And this mercury retains a positive charge in this bridged form. Something similar to this is actually the bridged bromonium ions. We know that bridged bromonium ions form in a similar way, where the bromine is also going to be positively charged. So in this next step, our water molecule comes in, as we see over here, and it's going to attack one of these two carbons. If you recall from bridged bromonium ions, this water molecule is going to attack the more substituted carbon. And when it does, it's going to break this bond between the carbon and the mercury. So now this water molecule used this lone pair to form that new bond between it and carbon. Therefore, it should only have one lone pair left. And we see that this bond broke between mercury and carbon, which leaves mercury only attached to this carbon over here. And we see that bond retained in this intermediate. Now, what's the charge going to be on this oxygen atom? If we quickly calculate the formal charge, it's going to be equal to valence electrons minus surrounding electrons. Oxygen has 6 valence electrons, and surrounding it right now is 1 from each bond and 2 from that lone pair. That makes for a total of 5 surrounding electrons. And 6 minus 5 makes for a positive 1 charge. So this oxygen here is going to have a positive charge. That leads us to our next step, in which water comes in again. And in this step, we have something called deprotonation. Proton is used interchangeably with hydrogen. And so if you are deprotonating something, you are taking a hydrogen away from something. So this oxygen is going to take this hydrogen away from this positively charged oxygen. And when it does, we're going to be left with this structure here. Notice how this oxygen regained its lone pair, so that now it has 2. And if you were to calculate its formal charge, which is equal to valence electrons minus surrounding electrons, it's going to be equal to 6 valence electrons, because we know oxygen has 6 valence electrons, minus 1 from each bond and 2 from each lone pair, which makes for 6 surrounding electrons. Therefore, 6 minus 6 is 0, and oxygen has no charge here. It is an alcohol group. Now, we can redraw this to look more like an alcohol group. It still has its lone pairs, we just haven't drawn them in. And now for our last step, we have the reduction part. Here is where we would be adding the NaBH4. We are actually removing the mercury acetate portion of the molecule. And in its place, we have a hydrogen. And of course, we have another hydrogen over here. We just haven't drawn it in, but it's been here all throughout the mechanism. So remember we said that this mechanism was called Oxymercuration Demercuration. So we see here in the beginning we're adding this mercurated group along with this oxy group. And in the end we are performing demercuration where we remove that mercurated group. Hence the name Oxymercuration Demercuration. So that's it for this video. If you liked it, please leave a thumbs up and feel free to subscribe. Happy studying!